What you see before you is the Andromeda Galaxy, our Milky Way's next-door neighbor. It is approximately 2.537 million light-years from Earth, and it is home to over 1 trillion stars. By comparison, the Milky Way galaxy is estimated to have around 400 billion stars.
But how much do we really know about each of those 1 trillion stars, or even the 400 billion of our own galaxy? After all, each and every one of those 1 trillion stars are virtually identical, and yet at the same time, so disparate a comparison seems nonsensical.
So, join us on our journey through the cosmos as we investigate one of the most intricate and diverse features the universe has to offer: the star. In order to understand the complexity of stars, we must first understand what makes a star a star. Stars begin as clouds of dust known as nebulas that are scattered throughout the galaxies. Turbulence deep within these clouds give rise to knots with sufficient mass that the gas and dust can collapse under its own gravitational attraction. As the cloud collapses, the material at the center begins to heat up. Known as a protostar, it is the core at the heart of the collapsing cloud that will one day become a star. As the cloud collapses, a dense hot core forms and begins gathering dust and gas. Stars are fueled by nuclear fusion of hydrogen to form helium deep within their interiors. The outflow of energy at the central regions of the star provides the pressure necessary to keep the star from collapsing under its own weight, and the energy by which it shines. However, stars don't last forever. When a star has fused all of the hydrogen in its core, nuclear reactions cease. This is the final stage in a star's life cycle. However, its remains continue to cause reactions in space. A supernova is one example, which is characterized as the explosive death of a star.
But, as we stated before, a majority of stars follow this cycle. However, some have major differences in composition that make them extremely unique, and some are even theorized to escape death. These are known as exotic stars. Exotic stars are hypothetical compact stars, or stars such as white dwarfs and neutron stars that are composed of something other than protons, neutrons, and electrons, and are balanced against a gravitational collapse by certain quantum properties. Now, for those wondering how anything can be made of something other than protons, neutrons, and electrons, this is because those subparticles aren't the smallest unit of matter. Just as we can break atoms down into protons, neutrons, and electrons, we can still break those particles down further. For example, protons and neutrons are made of 3 subatomic particles known as quarks, and even quarks are theorized to be able to be broken down further still. But here in our ship of the imagination, we aren't bound by the laws of physics. Here, we can explore whatever we wish, even the theoretical. We can shrink to subatomic size in the outer reaches of space to explore these exotic stars.
The first type of exotic star we'll explore is a quark star. After a normal star explodes in a supernova, a smaller, more dense star can form. The new star is called a neutron star. When the neutron star can no longer support its density, a second explosion, dubbed a quark nova, occurs. This creates a superdense star on the verge of transforming into a black hole. This new star is called a quark star.
A quark star is comprised of quarks that form when the neutrons break down under extreme pressure. Quark stars are hypothesized to have an iron shell with free-floating quarks inside the shell. Of all the types of exotic stars about to exist, quark stars have the most evidence behind them. In fact, although there is no definitive proof, there is evidence that the star 3C58, approximately 150 light years away, is a quark star due to its smaller than average size. However, these quarks are not the only strange type of exotic star. A second type of exotic star is also named for its composition, a group of hypothetical subatomic particles known as preons. Preons are theorized to be remnants of the Big Bang and make up what was once thought to be the smallest unit of matter, a quark. Once formed, a preon star would be anywhere between 1 meter, with an absolute mass of 100 Earths, to the size of a pea, with an absolute mass equal to that of the Moon. However, it would also have a density nearing that of a black hole. Preon stars, though hypothetical, create a measurable effect on the particles around it. Preons bend light, which creates gravity waves that draw lines of seismic shocks throughout the Earth's crust.
Preons themselves have still gone unobserved, however, as unlike other subhadron particles, which are particles smaller than a bundle of quarks known as a hadron, they cannot be seen inside of a particle accelerator and can only be observed after an event similar to the Big Bang, which would result in the creation of preon particles. However, it would also be catastrophic. Preon stars are one of the most elusive type of exotic stars, and yet at the same time propose incredible scientific ideas, such as the idea of a superdense subparticle, and that subparticle can't even be viewed by conventional means.
A neutron star is at the very tipping point of becoming a black hole. In these conditions, temperatures rise to a tremendous height, in which the weaker nuclear force and electromagnetism fuse together and create the electroweak force. This is the birth of an electroweak star. Physically smaller than neutron stars, electroweak stars are small and dense. Unlike a neutron star, these electroweak stars offset a tremendous amount of energy. Rather than breaking down the quarks, the electroweak field converts the quarks into leptons. Leptons are one of the basic building blocks of matter and are slightly smaller than quarks. Electroweak stars are, like most exotic stars, just theoretical, and no direct proof is available as of late.
Exotic stars are fascinating. Should any of them be proven to exist, it would challenge much of what we know today.
Everything from subparticles, laws of physics, and even a star's death would be in question. These stars differ from the average star so greatly in composition that several scientific theories and even facts may no longer be what they seem.